In the name of Almighty God, I'm Max Sankoshan. Today I want to talk about multibody dynamics module in Computer Multiphysics simulation software. Today I want to go to the fluid multibody interaction interface. Using the fluid multibody interaction interface, you can model phenomena where fluid and a rigid or deformable solid affect each other. The interface includes a predefined condition for the interaction and the fluid-solid boundaries. Arbitrary Lagrangian Eulerian formulation is used for incorporating the geometrical chains of the fluid domain. Use this interface if the geometry sequence is set up to form a union in multibody modeling. It is more common that the assembly model is used, in which case you should use the fluid multibody interaction assembly interface. Using a stationary or time-dependent study, the fluid multibody interaction interface models bidirectional coupling between solids and interface fluids. You add a predefined fluid multibody interaction interface from the fluid structure interaction groups in the fluid flow branch of the model wizards or add physics windows. Laminar flow and multibody dynamics interfaces are then added to the model builder. In addition, the multibody physics coupling node is added, which automatically includes the multiphysics coupling feature fluid structure interaction. At the same time, a moving mesh node with a deforming domain subnode is created under the definitions. For more information, see the deforming fluid domains. On the constituent physics interfaces, we have the laminar flow interface is described in the single phase flow laminar flow interface. When the CFD module is available, turbulent flow is supported through the inclusion of a number of turbulence models. The multibody dynamics interface is described in the multibody dynamics interface. The deforming domain feature is described in the moving mesh features. Now I wanna go through the settings for physics interfaces and coupling features. When physics interfaces are added using the predefined couplings, all specific settings are included with the physics interfaces and the coupling features. However, if physics interfaces are added one at a time, followed by the coupling features, these modified settings are not automatically included. For example, if single laminar flow and multibody dynamics interfaces are added, Computer Multiphysics adds an empty multiphysics node. You can choose from the available coupling features, but the modified settings are not included. Another difference is that the laminar flow interface added by the predefined coupling employs pseudo-time stepping per default for stationary models, while a standalone version uses an automatic Newtonian damping. The latter can sometimes give shorter solution times, which the pseudo-time stepping often gives a more robust solution procedure. You can disable the pseudo-time stepping in advanced settings. Sections for the fluid interface coupling features are available from the context menu. Right-click the multiphysics node or from the physics toolbar multiphysics coupling menu. Now I want to go through the coupling features. The fluid structure interaction multiphysics coupling is used to couple the interfaces. The fluid multibody interaction assembly interface. Using the fluid multibody interaction assembly interface, you can model phenomena where fluid and rigid or deformable solid affect each other. The interface includes a predefined condition for the interaction and the fluid solid boundaries. This interface is used when the geometry sequence is set up to form an assembly. Arbitrary Lagrangian Eulerian formulation oil is used for incorporating the geometrical chains of the fluid domain. Using a stationary or time-dependent as study, the fluid-solid interactions assembly interface models bidirectional coupling between the solids and fluids. You add a predefined fluid multibody interaction assembly interface from the fluid structure interaction group in the fluid flow branch of the model wizards or add physics window. Laminar flow and multi-body dynamics interfaces are then added to the model builder. In addition, the multi-physics coupling node is added, which automatically includes the multi-physics coupling feature, fluid structure interaction pair. At the same time, a moving mesh node with a deforming domain subnode is created under the definitions. For more information, see deforming fluid domains on the constituent physics interfaces. We have the laminar flow interface is described in the single phase flow laminar flow interface. When the CFD module is available, turbulent flow is supported through the inclusion of a number of turbulence models. The multibody dynamics interface is described. The multibody dynamics interface, the deforming domain feature is described. The moving mesh features. Now I want to go to the settings for physics interfaces and coupling features. When physics interfaces are added using the predefined couplings, all the specific settings are included with the physics interfaces and coupling features. However, if physics interfaces are added one at a time, followed by the coupling features, these modified settings are not automatically included. For example, if single laminar flow and multibody dynamics interfaces are added, Capsule Multiphysics adds an empty multiphysics node. You can choose from the available coupling features, but the modified settings are not included. Another difference is that the laminar flow interface added by the predefined coupling employs solo time stepping per default for stationary models, while the standalone version uses an automatic Newtonian damping. The latter can sometimes give shorter solution times, while the solo time stepping often gives a more robust solution procedure. You can disable the pseudo time stepping in the advanced settings section. For the fluid interface, coupling features are available from the context menu. Right click the multiphysics node or from the physics toolbar multiphysics coupling menu. Now I want to go through the coupling features. The fluid structure interaction pair multiphysics coupling is used to couple the interfaces. Now I want to go through the magnetic rigid body interaction in rotating machinery interface. The magnetic rigid body interaction in rotating machinery interface combines multibody dynamics and rotating machinery magnetic interfaces together with the moving mesh features. The parts models using the multibody physics dynamics interface can be either rigid or flexible. In the flexible domains, you can compute deformations caused by mechanical and electromagnetic forces in, for example, stator and rotor of an electric motor. It is also possible to compute the stress, in which case it is recommended to change the discretization for the displacement degrees of freedom in the multibody dynamics interface to second order. The magnetic rigid body interaction in rotating machinery interfaces are available for three dimensions and for planar two dimensions geometry. This is found under the rotating machinery magnetic structure interaction branch, under the electromagnetic structure interaction branch, within the structural mechanics branch. When this multiphysics interface is added using the model wizard, a multibody dynamics interface, and a rotating machinery magnet interface are added to the model builder. In addition, the multiphysics coupling node is added, which automatically includes the multiphysics coupling magnetic forces rotating machinery. On the constituent physics interfaces, the rotating machinery magnetic interface is described in the rotating machinery magnetic interface. The multibody dynamics interface is described in the multibody dynamics interface. The deforming domain feature is described in the moving mesh features. Setting for physics interfaces and couplings features. When physics interfaces are added using the predefined couplings, all specific settings are included with the physics interfaces. However, if physics interfaces are added one at a time, followed by the coupling features, These modifier settings are not automatically included. The full functionality of the multi-body dynamics and rotating machinery magnetic interfaces is accessible under the respective interface at the domain boundary edge or point level in the geometry. The participating rotating machinery magnetic interface by default adds an Ampere's law node with its selection set to all domains and the material type set to solid. This node serves to represent solid magnetic material domains. Any number of Ampere's law nodes can be added manually to the interface and configured to represent either solid or non-solid, for example, air or free space materials. The multibody dynamics interface by default adds a rotating frame node to model the effect of rotation to add the rotation to the definition of the spatial frame. The define spatial frame rotation checkbox is selected by default. Moving mesh chapter when a magnetic rigid body interaction in rotating machinery multiphysics interface is added using the modeling wizard, a deforming domain node and a rotating boundary node are added automatically to the model builder. These nodes represents domains and boundaries where the mesh can deform. By default, both nodes have empty selections under the deforming domain. You can select domains that represents non-solid magnetic materials such as air or fluid or free space. However, this is only needed if the boundaries of such domain experience significant change due to deformation or rotation of the adjacent solid domain. Otherwise, the moving mesh computations could introduce unnecessary overhead and nonlinearity in the model. See the form mesh fundamentals. Domains selected in the multi-body dynamics interface are not applicable under the deforming domain. You can also choose the mesh smoothing type, which is by default set to hyperelastic. More information about the smoothing type can be found in the deforming domain chapter in the Console Multiphysics Reference Manual. By default, the mesh is fixed at all exterior boundaries of the geometry. Use the rotating boundary node to select the exterior boundaries where the mesh can slide along the boundary. You can also add other types of boundary conditions for the mesh motion. For details, see moving mesh features in the Compton Multiphysics Reference Manual. Coupling features are available from the context menu. Right-click the Multiphysics node or from the Physics toolbar Multiphysics Couplings menu. Now I want to go through the couplings features. The magnetic forces rotating machinery multiphysics coupling is used to couple the interfaces. Now I want to go through the multibody dynamic story chapter. This chapter introduces you to the theory which is specified for the multibody dynamics interface features. In this chapter, we want to go through joint theory, camp follower theory, gear pair theory, rigid body contact theory. The first one, joint theory. In this section, we want to go through representation or rotation, prismatic joint theory, hinge joint theory, cylindrical joint theory, screw joint theory, planar joint theory, ball joint theory, slot joint theory, reduced slot joint theory, clearance joint theory, fixed joint theory, distance joint theory. Universal joint theory, theory for joint constraints, theory for joint locking, theory for springs and dampers on joints, theory for prescribed motion on joints, theory for applied forces and moments on joints, theory for friction in joints, theory for joint forces and moments computation. Representation of rotations in two dimensions models. The rotation can only occur around the z-axis. It is represented by a scalar angle theta. In the three dimensions, the situation is more complex. There are three rotational degrees of freedom. For finite rotations, however, any choice of three rotation parameters is singular at some specific set of angles. From the from this reason, a four-parameter quaternion representation is used for rotations in the joint. The quaternion parameters are called A, B, C, and D. These four parameters are not independent, so an extra equation stating that the following relation is added, such as a to the power of 2 plus b to the power of 2 plus c to the power of 2 plus d to the power of 2 is equal to 1. The four quaternion parameters are often represented as one scalar and one vector. where B is equal to the matrices as a column, only single column, B, C, and D. The connection between the quaternion parameters and the rotation matrix R is as R is equal to the first row of matrices is R to the power of 2 plus B to the power of 2 minus C to the power of 2 minus D to the power of 2. The next element 2BC minus 2RD. The next element 2RC plus 2BD. The next row is 2RD plus 2BC. The next element in the second row is R to the power of 2 minus P to the power of 2 plus C to the power of 2 minus D to the power of 2. The next element is 2DCD minus 2RB. The third row is 2BD minus 2RC. The next element in the third row is 2RD RB plus 2CD. The next element is R to the power of 2 minus B to the power of 2 minus C to the power of 2 plus D to the power of 2. The rotation can be also represented as a rotation vector which direction e theta and a magnitude theta. Theta is equal to theta e theta. The magnitude of the rotation is theta is equal to 2r to cosinus alpha, and the direction is e theta is equal to b divided by absolute b. The parameter r can thus be considered as measuring the rotation, while b, c, and d can be interpreted as the orientation of the rotation vector. For small rotations, this relation simplifies to theta is equal to 2 multiplied by the only single column for matrix B, C, and D. Successive rotations are represented by a quaternion multiplication such as follow. Just as finite rotations, quaternion multiplications are not commutative. The next theory is prismatic joint theory. The prismatic joint, also known as a translation or sliding joint, has one translational degree of freedom between the two connected components. The components are free to translate or slide relative to each other along the joint axis. Joint axis and its local coordinate system. The local coordinate system of a joint, which can be sent as rigidly connected to the source attachment, consists of three axes: joint axis E1, second axis E2, and third axis E3. To specify the initial direction, joint axis E10 using one of the following methods. Method 1, give the components explicitly in a selected coordinate system. Method 2, select one of the axes of a selected coordinate system. Method 3, select an angle edge that is parallel to the joint axis. For all methods, the axis is normalized to give a unit vector. In method 3, the direction that has a positive projection on the global x-axis is selected. If the projection on the x-axis is very small, the edge is almost perpendicular to the x-axis, then the y-axis is used in the projection criteria, and if the edge is perpendicular to the y-axis, then the z-axis is used as a joint axis. You can also choose to reverse the direction of initial joint axis. If the direction of the second and third axis are important, for example, when interpreting joint force results in the joint local coordinate system, or where there is elasticity in the joint, then method 2 is preferred because this gives full control over all three axes. When an axis in the selected coordinate system is chosen to specify the joint axis, the other two axes are determined through cyclic permutation. For method 2 and method 3, the initial second axis and initial third axis are computed internally as described below. The initial second axis E20 perpendicular to the initial joint axis is computed by making an auxiliary axis E auxiliary, an axis not parallel to the initial joint axis, and then taking a cross product of the initial joint axis in the auxiliary axis. E20 is equal to E10 multiplied by E auxiliary. The initial third axis E30 is computed by taking a cross product of initial joint axis and the initial second axis. E30 is equal to E10 multiplied by E20. Finally, the rotated axis in the form configuration are formed by rotating the individual axes using the rotation matrix of the source attachment or source. For two dimensions models, the generation of the coordinate system is significantly simplified. The initial third axis E30 is taken as the out-of-plane axis EZ. The initial second axis E20 is orthogonal to E10 and E30. You see, we have our equations. A20 is equal to AZ multiplied by A10. A13 is equal to AZ prismatic joint formulation. For a prismatic joint, the destination attachment is free to transfer relative to the source attachment along the joint axis. The add degree of freedom is thus the relative displacement along the joint axis. The rotational motion of the source and the destination attachment of the center of the joint can be computed as follow formulations such as U source is equal to R source minus I multiplied by XC minus XC source plus U source. UC destination is equal to R destination minus I multiplied by XC minus XC destination plus U destination, where for the source and destination attachments respectively, UC source and UC destination are displacement vectors for the attachment at the center of joint. R source and R destination are the rotation matrices describing the rotation of each attachment. R XC source and XC destination or the position of the centroid of the attachment. U source and U destination or the displacement at the centroid of the attachment. XC is a joint center. To formulate this kind of connection for a rigid joint, the motion of the destination attachment is prescribed in terms of the motion of the source attachment, such as USC destination is equal to USC source plus UR. BA destination is equal to BA source. This displacement vector U, the quaternion vector B for the source and destination attachments are defined as U is equal to UVW, B is equal to BCD. The relative displacement vector in the global spatial coordinate system UR is defined as UR is equal to UEA1. For two-dimension, the motion of the destination attachment is prescribed in terms of motion of source attachment such as USC destination is equal to USC source plus UR. Phi destination is equal to source, where phi is the rotation about z-axis out of plane axis. So next is the joint elasticity in prismatic joint. In the case that the joint is elastic, the elastic displacement and rotations are added to the source motion so that the displacement and rotations at the center of joint is no longer equal for the source and destination attachments. You see, we have a UC destination is equal to UC source plus UA1 plus UR, where destination is equal to B prime. The elastic translation and rotation vectors are expressed in terms of the joint axis as follow. Here, year 2, year 3, theta 1, theta 2, theta 3 are the default elastic degrees of freedom available for this joint. Optionally, only a subset of them can be chosen to the elastic. The quaternion representing the elastic rotation is as EA1, BA1 and can be computed from the elastic rotation vector to tell you about the spring and damping forces and moments are proportional to the elastic displacements and velocities. The spring and damping matrices are subdivided into four parts depending on whether they relate to translation or rotation. The matrices which group translation and rotations option in the input data. The total elastic joint force and moments can be written using the spring and damping forces as and moments as follow. The contribution to the virtual work is such as delta W is equal to FA1 multiplied by delta A1 plus MA1 multiplied by delta T1. Thank you so much for watching my tutorial video until then. Today is the 8th day of the June 2026. Time is 12:39 in the morning. Also, you can download the proper and related quantum physics simulation file from github.com/masterscript.